Hey everybody, welcome to day 2 of virtual learning spring edition. I know that you guys, especially those that had me last trimester, really miss all the ed puzzles and everything, so I'm happy to bring those back to you today. And hopefully we don't have to get used to doing this and being virtual, but this is where we're at right now. So when we have new lessons, then this is what we will be looking at, is some ed puzzles today. And I mean, one note with these ed puzzles, I'm going to do my best to make them quick. I understand you don't want to sit here and watch a 30-minute video, but also you have to understand that in order to get through this material in a way that's effective, you should plan on it being about a 20-minute video here. So get comfortable, grab your notes, and be ready to write down a few things. Today we're looking at properties of trapezoids and kites. So a few properties, and then we're going to be looking at some examples. Our goals today: students will be able to use properties of trapezoids and kites. Students will be able to use the trapezoid mid-segment theorem to find distances. So really 2 learning targets there. First, let's look at some terms. When we hear the word trapezoid, we have a pretty good idea of what a trapezoid looks like, right? If I were to ask you to draw a trapezoid on your paper, it would probably be something that looks like this, which is correct. But here are some more specific things of what we look for geometrically and lengthwise and different things like that with a trapezoid. So a trapezoid is a quadrilateral, so 4-sided figure, with exactly 1 pair of parallel sides. So those parallel sides we call the bases, okay? Now, one thing to watch out for, if they draw a trapezoid like this, it tells these are the parallel sides. These are still our bases, here and here. These 2 lines are not the bases just because it's the top and bottom. So pay close attention. They might try to trick you and rotate the object, but our base, no matter how the object is rotated, is still the top and the bottom. The base angles of a trapezoid are the 2 consecutive angles whose common side is the base. So our base angles, A and D, and B and C, then would be the other pair of base angles. The non-parallel sides are the legs. So we're familiar with that term. We have the term leg with right triangles and different things. But the non-parallel sides, when we're talking about a trapezoid, are the legs. Now, when we look at trapezoids as a whole, we have a specific type of trapezoids, and that's an isosceles trapezoid, meaning that the legs are congruent. So the legs in a trapezoid do not have to be congruent, but if they are, then it is an isosceles trapezoid. And that says rhombus corollary. That is from the last lesson. So in this example, show that this is a trapezoid, then decide whether or not it is an isosceles trapezoid. And we do this by going back to the same old stuff that we've been talking about over and over again. And that is by using the slopes of lines, and we also will be using the distance formula a little bit. Now, in this video, I am not going to go through and solve for the distance formula. I'm going to just tell you that by using the distance formula, you'll find that the length of ST is blank. And I will just write the answer. I'm not going through choosing points and solving the square roots. I'm not doing all that right now. I'm just going to give you the answer. We should know how to do the distance formula at this point and should know how to find slope and all that at this point. So but what I am going to go through is the steps we need to use to show this. So the first thing that we need to do to decide whether, or to show that this is a trapezoid, is compare the slopes of all opposite sides. So compare slopes opposite sides. I guess I could add of in there. That wouldn't be difficult. Compare the slopes of opposite sides. So our opposite sides, why don't we start with the top, RS, and OT. So the slope of RS is 1/2. The slope of OT is also 1/2. So that's a good start. That's good news. So that means we have equal slopes here. Do we talk about slope? Oh, I forgot to mention one important thing for why the slope matters. Our bases are parallel. The tick marks are on there, or the little triangles are on there. I forgot to point that out, but our bases are parallel. So that is why it's important that when we look at these two, what look like they are the base, these lines need to be parallel for us to have a trapezoid. So that's the first thing that we need to look at. And then those need to be parallel. Then if we look at the other set of slopes, we have RO and ST. The slope of RO is undefined. You can see it's right on the y-axis. RO is right there. It is undefined slope. And ST is -1. So we're all set there. I mean, those obviously don't need to have the same slope, but we still need to check those opposite slopes there. Step 2 would be that we need to check to see if it is an isosceles triangle. So to decide if it's an isosceles triangle, we need to look at those legs. So we need to look at the length of the legs. So that would be RO. RO is 3 units. And ST, after doing the distance formula, we find that ST is 8 units. So they're fairly close in length, but they're not the same. So we do not have an isosceles trapezoid. All right, so 2 parts of this question. Show that it's a trapezoid, which we did up here in the blue by looking at these slopes. And then to decide whether or not it's isosceles, we need to look at the lengths of the sides, like we did here. If the lengths are the same, then we're all set. We have isosceles. If they're not, then it is not an isosceles triangle. Let's look at a few more theorems that have to do with these, all with isosceles trapezoids. I think I said triangle a couple times earlier. Yeah, but I meant trapezoid. Isosceles trapezoid base angles theorem. If a trapezoid is isosceles, then each pair of base angles are congruent. Well, that makes sense. That if we have these legs that are congruent, an isosceles trapezoid, then the base angles are congruent. So B is congruent to C, A is congruent to D. If a trapezoid has a pair, we're looking here now. Sorry I didn't give the theorem name or the theorem numbers on here. You could look at that in your textbook if you really want to know. Isosceles trapezoid base angles converse. So on the other hand, if a trapezoid has a pair of congruent base angles, so if we have a pair of congruent base angles here, then we know we have an isosceles trapezoid. So that would mean that these are, we know these are congruent. We know that these are also congruent. Sorry that there's the apostrophe thing over the O in isosceles. Google kept wanting to autocorrect to that, and I kept telling Google no, but it looks like Google overrode me on that one. Sorry. Super unprofessional for me to have typos in here. Anyway, last one. Well, I mean, let's go back to that second one. If we have those pair, I mean, we're looking at the converse of the base angles theorem. If they tell us that those bottom angles are congruent and we have congruent sides, then we can know that we have an isosceles trapezoid. The third way we can know we have an isosceles trapezoid, or a trapezoid is isosceles if and only if its diagonals are congruent. So AC would be congruent to BD. We've looked at the diagonals a bunch of different times with different shapes, so this shouldn't be a surprise that they bring up the diagonals here. And I mean, it makes sense. If these legs are the same, that the diagonals would be the same. Notice it does not say anything about the angles that are split. Like, it doesn't say that this diagonal splits angle D or bisects angle D, so we're not going to assume that right now or anything like that. We just know that the diagonals in an isosceles triangle are congruent. The stone above let's look at an example. The stone above the arch in the diagram, this diagram, is an isosceles trapezoid. So they tell us up front it's an isosceles trapezoid. We need to find the measure of each angle. Well, if we know it's an isosceles trapezoid, we have our base on bottom and top. So that means we know that this side and this side are congruent. So that has to be 85. Now, we also know this is a four-sided figure, so we know it needs to add up to 360 degrees. So we have two sides that are both 85, so that would give us a total of 170 degrees. Now we know that angle J and angle M have to be congruent because it told us up front we have an isosceles triangle, and that was one of the theorems, this first theorem that we looked at with isosceles trapezoid. I keep saying triangle. Trapezoid. So if we just say that angle M, we say this is x and this is x because they both have to be the same thing. So plus 2x, and we could find M and J. 360 minus 170 would give 190? No, that doesn't seem right. Let me think. Oh, no, 190 might be correct. Yeah. $95. So we could find each of those angles of the trapezoid. I know I went kind of quickly through this example, but I think we've been doing things like this for a long time, finding the angles of the interior angles of different shapes, and solving for those. Let's look at a new term and a new idea: the mid-segment of a trapezoid. The mid-segment of a trapezoid is the segment that connects the midpoints of the legs. So we know that we have a leg and a leg, and the mid-segment, it makes sense, connects the midpoint of that leg. Now, or of those legs. We're going to look at some relationships that the mid-segment has with other parts of the triangle. So that's where it's going to become important. But we need to recognize and know what it means to have a mid-segment in the trapezoid. So the mid-segment theorem. The mid-segment of a trapezoid is parallel to each base. Well, that makes sense. So that shouldn't be a surprise there. And its length, here's an important thing, its length is 1/2 the sum of the lengths of the bases. So if we said that this was 10 and this was 22, we could find Mn equals 1/2 10 plus 22. Okay, so that mid-segment is add up the bases, divide by 2. So in the diagram, Mn is the mid-segment of the trapezoid. Find Mn. So Mn equals 1/2 of 12 plus 28. Mn equals 20. No big deal. Now here's where we get a more complex example. Find the length of the mid-segment of YZ. Now, I could totally see sitting in class and someone raising their hand and saying, why can't we just look at point Y, look at point Z, and use the distance formula? Well, the problem with that is it looks like we could probably tell where point Y is, right? Y looks like it's at 4, maybe at 4, 8 right here. But point Z, we're not sure where that is. I mean, maybe that's at 7, 1, maybe we don't really know. We can't really tell. So we can't just use those points and guess and hope for the best to find what that mid-segment is. But we do know for sure TU and SV. We know right where those points are at. So we could find the distance of each of those. And I'm not going to go through the entire distance formula right now, but I'm just going to tell you TU is the square root of 80. SV is the square root of 20. And we know we can find YZ by doing 1/2 root 80 plus root 20. Now, you could plug this in your calculator and you could get a decimal, but if it asked you for a clean number, which I could see like Big Ideas doing, or even on a test or a quiz or whatever, then I might not want you to round to a decimal place. We're kind of working on our square roots as well. So we could rewrite and simplify square root of 80 to be, 4 square roots of 5. Square root of 20 is 2 square roots of 5. We can add them together. And if we were to write it in simplest form, the distance of YZ would be 3 square roots of 5. Or find the length of the mid-segment would be 3 square roots of 5. So I wouldn't give you a ton of examples that look like this one where you have to simplify the square roots because I know it's kind of a pain, but also to have a couple of them is a good review. A couple more theorems, one more example. Definition first. A kite is a quadrilateral four-sided figure that has 2 pairs of consecutive congruent sides, but opposite sides are not congruent. So in our kite, we have consecutive congruent sides, one than the other, but these opposite sides are not congruent. That is our definition of a kite. So when you go to the beach and you see somebody flying one of these, oh, that's a terrible drawing. One of these box kites, you can tell them you cannot call that a kite because a kite is a quadrilateral that has 2 pairs of consecutive congruent sides, and the opposite sides are not congruent. So when you see little Timmy at the beach flying his kite, then you got to tell him, hey, that's not a kite, you're flying a box. Anyway, bad joke. Let's look at some theorems and some rules that we have with kites. First one is looking at the diagonals. If a quadrilateral is a kite, so if we have a shape and we think it is a kite, then its diagonals are perpendicular. So we can see that these diagonals intersect and create a perpendicular angle there. So that's one way that we know for sure that we have a kite. The other thing to look at when we have a kite, if a quadrilateral is a kite, then exactly 1 pair of opposite angles are congruent. So only 1 pair of opposite angles are congruent. Not 2 pairs, just 1 pair of opposite angles. Last example. Find angle D. Well, if we're looking at angles in this kite, well, total interior angles of this kite, we know it has to add up to 360 degrees. They tell us that one angle is 115, another one is 73, and then the theorem we just looked at said that 1 pair and only 1 pair of opposite angles in a kite are congruent. Well, 115 and 73 are not congruent, so that means that D and F need to be congruent. So let's say that we label them both X because they need to be the same thing. We have 2 X's, and we would find that X equals 86 degrees. So measure of angle D would be 86 degrees. So that would be applying that second theorem that we looked at here. Now you could see where they would ask you questions about these diagonals and how they are perpendicular, but I'm not going to look at too many examples of that right now. The last thing I want to show you is this is kind of a big picture thing to check out. So we've been talking about quadrilaterals, right? Four-sided figures a lot. We've looked at parallelograms, trapezoids, and we just looked at a kite. Underneath parallelograms, we have two different types, rectangles and a rhombus. When we have a rectangle and a rhombus put together, that gives us a square. And we have two different types of trapezoids, just regular trapezoids, and specifically isosceles trapezoids. So this kind of gives us a good view of what we're looking at. Big picture, it wouldn't be the worst thing to write down in your notes, but again, you would not have to. It just shows where we've been the last couple of lessons. So sorry for the length of this first lesson. I know that it's a long time to be watching, but we need to get this information across, and we need to keep moving forward, even if we are virtual. So hope you guys are doing well.